Okay, so now at this stage in the class, we need to start considering things that have nitrogen in them. And so far, we've mostly focused on carbon metabolism. You know, carbohydrates and fats have primarily carbon in them, and of course, oxygen and hydrogen. But they're primarily, the metabolism is primarily understood in terms of oxidizing carbon and reducing carbon back and forth. And we've seen nitrogen in just cofactors and certain other compounds, but really there are a lot of compounds, the amino acids and the nucleotides, that have nitrogen. And nitrogen is a very important molecule. Now, what we want to consider here is how do we get inorganic nitrogen from the environment, into metabolism. As animals, we mostly eat our nitrogen-containing compounds, our amino acids and nucleotides, as food, and we don't use those compounds too much for energy. We use them to get the nitrogen, to put them in our nitrogen-containing compounds. But many organisms, such as plants and bacteria, have to get their nitrogen not from food, but from the environment. And note, we're not considering the process by which we get elemental nitrogen, gaseous nitrogen from the atmosphere into it. That's a much more complicated process, and we might consider that later on in the semester. But it's really not fully understood yet how that works exactly. What we're really just going to consider here is, you know, a much simpler process by which we take inorganic nitrogen. By that we mean ammonia. Environmental nitrogen that's readily assimilatable by plants and microorganisms is in the form of ammonia. And some microorganisms can assimilate nitrate too, and there's a process that all goes through. The nitrate gets converted to ammonia first. Okay, so we really want to think of this in terms of nitrogen carriers. Okay, and so I'm going to, sort of draw this. There's sort of there. We have our empty nitrogen carrier, and then we have, our level, just like electron carriers. Okay, we have two different types of electron carriers and two different energies, and we can really think of them here. So we have high energy electron carriers such as NAD and a low energy such as FAD. Here we're going to have two different levels of nitrogen carriers. We're going to have this one here, our sort of standard nitrogen carrier at sort of moderate energy, moderate nitrogen potential. And then we're going to have our high energy nitrogen, which we're only going to use if we really have to, because it's too expensive. And we're going to see how much it costs here. Okay, and H3. Okay, so, and they're going to come in, they're going to go from NO to N1, and I'm going to, take you through this process here. And the first thing is to know what these compounds are. Okay, so here, I'm going to draw them, and you should hopefully know what these compounds are, where they come from. For instance, this compound right here. You've seen this compound several times before. And this compound here, if you recall, one of the amino acids. Hopefully you know which one. And then this compound, another of the amino acids. Okay? And if you look at it, they have the same backbone, the same 5-carbon chain, 2 carboxylic acids. And what we do is we count. There's no nitrogen atoms. There's one nitrogen atom, and there's 2 nitrogen atoms. This nitrogen's at higher potential. It's going to take more energy to make it, and we're going to transfer it when we want to really put nitrogen into something at a higher potential. Okay. Now, just as we don't draw the full structure of ATP when we're going to use ATP as a phosphate transfer, we just say A and it transfers its phosphate, or we don't draw the full structure of NAD when we use it as a reducing agent, or NAD plus when we're using it to accept electrons. We just use the symbolic form of it. Here, in the same way, when we're using these compounds to carry nitrogen, I will allow, and in fact, I will encourage, I would prefer you do this. Oh, of course, you can draw the full structure. I would prefer you to use the abbreviations, just like I prefer to use, the abbreviations for ATP and the abbreviations for NAD. Okay? And so this is one reason why you need to know these abbreviations, right? It'll save you a lot of effort in our nitrogen pathways. You can just say alpha-ketoglutarate, you can AKG, E, and Q. Okay? And you should recognize these things as nitrogen carriers. Okay? So how do we get these things into here, first of all? These are obviously, these are in metabolism. It's going to take some energy, right? And you have your sort of primary forms of energy. You have ATP and you have NAD. And we know that NAD is worth more energy than ATP. Okay? So how are we going to get these in? Well, the first thing we need to consider is some nitrogen chemistry. And the most important is a Schiff base. Okay, so a Schiff base is where we take some kind of nitrogen compound, okay, and we react it with our favorite compound in biochemistry, a carbonyl. Okay, so what can happen when this reacts here? Here, we can do this type of chemistry. I'm going to put on the hydrogens here to be explicit here too. So this is going to be, let's say, NH2. Okay, and therefore it's nucleophilic. If it was NH3, that would not be nucleophilic because it would be positively charged, right? And positively charged things aren't nucleophiles. And it would also have no lone pairs, so it has to be the free base form to be a good nucleophile. Okay, and that's going to take out, and what we're going to get here, I'm going to transfer this onto some proton here. Okay, some proton here, and we're going to get nitrogen. Okay. Now this is now a tertiary nitrogen now. Here. It's a quaternary nitrogen, I should say. It has these things here. So this is now going to be NH plus, right? Because it has those two things on it. And then we're just going to in fact, let me put the protons on in black here, because we're making kind of a point of it. Now this is going to deprotonate, and we're going to get N. Okay. And now what can happen is this can collapse here now, like this, and we can kick out this. Okay. So here we're going to get, and we put this hydrogen on still there, so we're going to get this compound N with an H on it, and we've lost OH, and now this thing, this is a shift, this is what's called a shift base right here. This thing right here, shift base. Okay, shift base means nitrogen, double bond, carbon. Okay, and then of course this thing will now deprotonate. This has a very low pKa. Okay, the pKa of this is about maybe 9 or 10 for a primary amine, right? pKa of a shift base is only about 4 to 6, around 5. So this is going to deprotonate, and this is this first proton we picked up. So these protons kind of cancel. Right here, we've added a proton right here, and we've released that proton. Whereas these molecules here, this proton and this is a dehydration. These two things together form water. Okay, you can really see that as a dehydration. These two protons come off, and then oxygen comes off, and we get them joined together. This is such a common thing, and it's reversible. This goes in both directions. We have a short form when we're going to do lots of mechanisms with this, and you got to get used to it. So you can draw this whole thing out. Takes you many steps. You won't get any more points than the person who writes. Okay, and you have to just sort of see this. This is kind of a short form. It's like a contraction. Okay, there, and we leave water. Okay, and we get there, shift base. Okay, this is going to happen so often, and then this can go in both directions. We can take water. If we want to go backwards, we would show the hydrolysis with water. We would just go like this. Okay, and that would come to, okay, this is going to be allowable shorthand, and I recommend you get familiar with that. Okay. And this happens non-enzymatically, as well as there are enzymes that can catalyze these reactions to make them faster. But this is such a rapid process. It's like the ring formation in carbohydrates. There are enzymes that will break open a carbohydrate pyranose ring, and there are enzymes that will like hydrate carbon dioxide in water. On the other hand, carbon dioxide will react with water by itself. Amines in solution with ketones or aldehydes will react spontaneously to form these things. Okay, and this is a big part of browning, for instance, in cooking. Is things like this happen. Okay, so let's look at this first thing, what happens here. Okay, so let's look at this first reaction here. So we have here, this is called glutamate dehydrogenase reaction. Oh, so what is dehydrogenase? What happens here? Well, what we can think of is we have the nitrogen NH3, and we have alpha ketoglutarate. And when we do the mechanism, we have to show all the structures. In a pathway, we don't. Okay, so what's going to happen here is this thing is just going to basically attack here, and we're going to get this compound as an intermediate, the shift base. And this is reversible. It's going to be an equilibrium process, and this is not really in because it can go back and forth. And this happens kind of non-enzymatically. What the enzyme does is now we're going to take this and we're going to reduce it. And if we put in electrons, we think, have we seen anything like that before? Well, for instance, sure we have. We have, for instance, seen this process, right? Where we want to go backwards here, relating malate to oxaloacetate, right? There we go. So we've seen lots of these processes here. Okay, we put in electrons and we change this carbonyl to an alcohol. If we put in electrons, we change this N. So an oxygen with a double bond, when we reduce it, becomes a single bond, an oxygen. Same thing here. When we put in the electrons, we're going to reduce this, and you can check by formal oxidation numbers. Right, there we go. There we go. Okay, so we can come to this first reaction, and we can recognize that this one here requires this. Okay, so we're going to use energy in NAD. Okay, and this is roughly, you saw in the electron transport part of the class, this is worth about 3.5 to 4 ATPs. So that's a very expensive process. We're using really 3 to 4 ATPs to get nitrogen into metabolism, into E. Okay, the next process that happens, we kind of do this. This is kind of an intermediate in here. Okay, the next reaction that we have here, we're going to take our. What we have to do is we're going to put it in here. Here's E, glutamic acid. We're going to phosphorylate this with ATP. And we know that these compounds, we've done this in, have we ever done this before? Sure. For instance, we have 3-phosphoglycerate. We just saw that in the Calvin cycle. We saw that a long time ago in gluconeogenesis, right? And we're going to get we're going to put the acyl phosphate, a high energy compound. Here we go. There we go. Right here. We've seen this lots of times, and we've seen other examples of ATP phosphorylating it. So we're going to get this kind of compound, a high energy compound, that's kind of an intermediate. And then, of course, the nitrogen is going to come in this step here. Here's where our NH3 comes in. Okay? And it displaces a phosphate. Just nucleophilically attacks here. You could imagine, you could hypothesize what the tetrahedral intermediate will be like, right? And we saw that in the dehydrogenase reaction. And we get simply, okay, so here, and you can check that, okay, so this is going to be here, A, okay. You can check that by the formal oxidation state right here. The formal oxidation state, this is going to be, let's write up here, this is a carbon joined to 2 oxygens, right? So this is going to be donating its 2 electrons. It's going to be a +2, whereas this carbon here is going to be 0. And this carbon here is going to be 0. And even on top here, this is going to be, right, this is going to be a +3. And this is also a +3. Okay? So you can tell that we must put in 2 electrons to cancel this +2 to make it a 0. Whereas going from +3 to +3 has no electrons. Okay, so you may think this is a little odd. We're telling you that this is the high energy form of nitrogen, and yet we're putting in ATP to make this, so that makes sense. We're putting in energy, but here we're putting in N, and we know that N is worth more than A, so how is this a higher energy form of nitrogen? That doesn't make any sense. Well, that's not really how this reaction is used, okay? So what it turns out is that there's a second enzyme. So this is the 2 things. This is called glutamate dehydrogenase, GTH, and this is called glutamine synthetase, okay? There's another enzyme, and you don't have to know those names. I'm not going to make you memorize those names, but you may read about this in a textbook, though. There's another enzyme. We think, okay, so we have nitrogen. What if we have? There's a way to kind of equilibrate these things, and this is just like adenyl kinase. Okay. Okay. So we have this thing here. There is, in fact, we discussed this in where we use 2 ATPs in some cases. We have an enzyme that does this: ATP plus AMP goes to 2A, it's an equilibrium process, ADP plus ADP. Okay? And sometimes we write this as AMP, ADP. There. We could write the same thing as this enzyme. It equilibrates the 3 levels of energy. ATP, we can think of ATP as the highest energy, ADP is the second highest, and AMP is kind of a totally empty form. Here, we can do a very similar thing here. There's an enzyme here that takes alpha-ketoglutarate and Q, okay, N0, you can kind of think of this one as N0, N2, and we're going to equilibrate this to E. Does this enzyme require any ATP or NAD or what? Okay, what do you think? Well, you can figure that out. Where's the picture here? Here, okay? Here, if we take a Q right here, this is also a +3. Okay, so all the atoms are the same. I can see this is +5 and this is +3. So I take a +5 and a +3 and I end up with 2 +3s. I must have to add. You can add them up, right? We must have to add in some electrons here. Okay, you can always tell. Okay, there you go. So this enzyme is called GOGAT. Glutamate oxoglutarate aminotransferase. Big long name, you don't have to worry about that. And I'm just telling you these names so that you can recognize them if you want to look this up in a textbook or something like that. Now this does not really assimilate nitrogen at all. But what we do when we're using this to assimilate nitrogen is we take the nitrogen in this step here, in the QS. Okay, so I take NH3 here and put in ATP here. Now, what's the overview of this pathway? This is like a very short nitrogen assimilation pathway. Okay, here I can tell you this. This has high affinity. So this enzyme here, where's my green? Low affinity. High affinity. Essentially, it has low affinity because this process is a reversible process. This enzyme, this shift base can form, and then it can break off very easily. Whereas this forms a very high energy phosphate, and when this nitrogen comes on, it's covalently bound, and it's essentially irreversible because we break in this high fast. So this is very high affinity process, and this is a low affinity process. Now, most organisms grow in areas where there's not much available nitrogen. Right? Plants, it's a very common thing for plants to be nitrogen limited, and microorganisms to be nitrogen limited in the growth. They have enough, plants have enough sunlight most of the time, and if you really want to make your plants grow, you fertilize them with nitrogen, and in some cases phosphorus. They need phosphorus to grow too. Those are the primary ingredients. So they can't use this pathway because there's not enough nitrogen around. They have to use this high affinity pathway. But this high affinity pathway, they need most of their nitrogen in the form of E, so we put it in this way, and we go to Q, and then we reproportion it to E. And from E is where most of our nitrogen comes. Okay? To most compounds. And this is only to a few compounds. We'll see examples of that just in just a minute here. But there, I want to talk, what is this overview pathway? So an overview pathway, we just look at what do we put in, what do we get out, and what does it cost, right? So what do we put into this pathway? Well, we have to put in anything. The E, right, we're taking alpha. The Qs are all, we form Q, but we use Q. So Q isn't in there at all. Really the overview. And this is sometimes called the glutamine synthetase plus GOGAT pathway. That's why I'm telling you the name if you want to look this up. The overview of this is really just alpha-ketoglutarate goes to E, right? We produce 2 E's, we use 1 E up, so we have 1 X over E. We put in ammonia right here, and in the process we put in this and this. It does the same thing as glutamate dehydrogenase. You can compare, there you go. You can compare these two reactions, okay? These do exactly the same thing, except when we use these two reactions on this overview mode to use the GOGAT plus glutamine synthetase, we do a reductive and a reductive plus ATP. We're putting in extra energy. And this one, plants and microorganisms can use this when there's sort of low amounts of nitrogen around. So in most of the time, this is a pathway that's used. Okay? Okay, so then when we talk about shifting to other compounds, let's look how nitrogen is then kind of distributed. And to do that, what we need to do is we need to learn one more cofactor. Yay, another cofactor. We only have, I think, 4 or 5 left. And this is called PLP. Okay? Oh, this pen, where's my blue pen? There it is. Pyridoxal phosphate. Okay, and what do you need to know about this? Well, this looks kind of, we've seen this before. Okay, this looks starting to look like a little bit of NAD. Okay, except it's not substituted, and that's very important. Remember when you want to get your, B level understanding of NAD. Let's put it up here. For NAD, right? I insisted that you draw. This is the B of NAD. Okay? And what you need to do is you need to show this substitution of this positive charge. This is not a substituted pyridine. It's just by itself. That's the pyrid part of it. And pyridoxal means there's an aldehyde. We put up here there. That's the B level understanding of PLP. That's what you absolutely need to know, and this is how it's going to work. And you're going to imagine it's going to work very similar to NAD in many ways, because it looks just like NAD. And then the rest of the molecule, if you want to learn, it looks like this. There we go. All right, so that's PLP, and PLP works. It's the single most important cofactor when we're dealing with amino acids, and these nitrogen carriers are in fact amino acids. And so this carrier is going to be crucial for another reaction. Now, the first reaction, so this way that we're getting to most other compounds, is called transfer of amino groups, transamination. Okay. Now, transamination. Here's the transaminase mechanism. We're going to take some sort of, I'm going to draw it with glutamine. Okay. So here we go. Okay. And PLP. Okay. Once again, in a mechanism, we just draw the core structure of the cofactor. We don't have to draw the whole cofactor, just like we don't have to draw all of TPP. Okay. So what we can do is, of course, we're using our shorthand. Right? Now, you could draw. This is what I'm saying in a mechanism. Where'd it go? Way back here. We talked about shift bases. I could draw all these individual steps if I want to, right? And you won't get any more points. And so I recommend that you start doing this as a shorthand because it happens so often. It's so tedious. Okay, and so what always happens with PLP is we form the shift base. Okay, here we go. Okay, and then what we're going to do is, now we can do some chemistry on this thing. We can take this, once again, this is going to be sort of a ping pong type of mechanism. We're going to take some base right here, and we're going to pull off this alpha proton right here. Okay, so let's look what we get. And then we're going to come into NAD, or not NAD, into PLP, but it looks like NAD, and you've done this so many times. Now here we're not going to a positive charge, so it's not going to grab the electrons and hold them forever, right? But what it's going to do is going to pull them that way, and, right, so this could have a proton or not on it here, and what we're going to get is, in the next step, something that looks just like NADH. Okay? We've kind of flipped the shift base. That's the point of this. We've flipped the shift base. Okay. Now, this can hydrolyze. I can show this right here. As I said, when we hydrolyze the shift base, we just show water attacking it. And we can show this reverse reaction all the way through, right? Or we can just go like this, and we can show it hydrolyze into the empty form. Okay? Alpha ketoglutarate. It's lost its nitrogen. It's kind of stuck its nitrogen on here, and what do I get? Oh, I have this compound, which is called pyridoxamine. Okay? Now, I can do this, and I can take some other alpha keto compound. So, let's take another alpha keto compound. Here's an alpha keto compound you may be familiar with. Pyruvate. Okay, so what can I do here? Oh, sorry, I drew this wrong. There we go. Yeah, for sure, I drew this wrong there. Make sure you do that one right. All right, so now we have this amine, and here, what's going to happen? We have an amine. It's going to form a shift base. Okay, and we're going to get let me just get my blue pen. Okay. Okay, and then this is going to go backwards. And there was this base that picked up that proton that's been sitting around right here on that base. It's the acid. And what do we get?